Hello, today I'd like to do a very simple Solidworks motion analysis example using a pair of gears. Here's the gears we studied in class. A very simple input gear, spur gear, 18 teeth. It's a 3-inch pitch diameter, 3/4 of an inch on the face width, and the diametral pitch was 6 teeth per inch. The output gear had 72 teeth, 12-inch pitch diameter, also 3/4 of an inch face width, and also had to have the same diametral pitch. The input gear was running at 12 RPM, and it needed to take about a 3,000 inch-pound torque. And the output gear rotated at 3 RPM and needed to take about a 12,000 inch-pound torque. So the gear ratio for the gear pair is 4. And in class, I think we calculated actually the horsepower for both gears together. In class, we had 1.14 horsepower. So looking at just the 1/2, that looks like about a 0.57 horsepower is what we're looking for. So what we're going to do here is we're going to go to a website I use. It's called rushgear.com. We're going to use the specs I just gave, and we're going to double check the performance using their horsepower calculator. We're going to download some SolidWorks files for those gears from rushgear.com. We're going to go into SolidWorks and we're going to create a simple assembly using those gears. Then we're going to launch a motion analysis on that model. And we're going to study something that's pretty cool. It's solid body contact between the gears, and then we're going to validate the performance of the gears in the motion analysis study. Okay, let's get to rushgears.com. So they've changed their website a little bit recently. I'm going to click here to build custom 3D CAD models. Let's do that. See where we go. Create a new part. Let's do that. Let's create a new part. I want to do a spur gear here to be consistent with what we were looking at earlier. In the past, I've used an 1141 that has hardened teeth, and I think that now that'll be cold formed, and I think the 24 to the 29, that must be a Rockwell C. So let me stick with that. Diametral pitch is 6 for the gears. Pressure angle 20. So do that. Number of teeth is 18 for the pinion. Bore diameter. Let's go with 3/4. I didn't mention that earlier what that was. Let's go with that. Let's go face width. Let's change that to 3/4 of an inch. I'm going to go without a hub. And let's see. I'd like to have a keyway. I'm going to go with a keyway right there. Click that, and it wants me to select width and depth. I'm going to use default size there for now. So it looks like 3/16 of an inch. Okay. So looks like I have something going here. Let's look at horsepower and torque. Okay, so it says type of load is uniform. I'm going to leave it as that. Intermittent, 3 hours a day. Let's leave it at that. We've got our diametral pitch is set for a spur gear, so we're good there. 12. I'm going to change my RPM here to 12. And this is calculating the load at the pitch line. And it's giving me safe static stress, velocity, the feet per minute. Horsepower, looks like I'm coming up a little bit short at 0.51. I think I was looking for 0.57. And my torque is also a little bit low. I could go back and tweak this later, but let's hold on to this for now. Okay, I'm going to try to download this now. Let's see what happens. Assigning a part number. SolidWorks Part Assembly 2013 Plus. Let's try to get the 3D file and see what happens. Okay, looks like it's built a part for me. Show it in the folder, and then go cut that and put it in my working gear example directory. So kind of have that. So that's good. Let's go and create a new part and go get my other guy. So right now I want diametral pitch of 6 again. Pressure angle 20. Number teeth 72. Bores 3/4 okay. Face width 0.75. Go ahead and put my keyway back in there. Default. So I have all that ready to go. Let me look at my horsepower and torque. Uniform, intermittent, diametral pitch the same. RPM now is 3, not 13. 3. And it looks like my horsepower actually is okay for the bigger gear, which is not surprising. I'm above the 0.57 I needed before, and I have more than the 12,000 inch-pounds that I needed. So we're actually pretty good on this gear. Okay, let's download that guy. Get file. Okay, within SolidWorks I've created an assembly, and I'm going to bring in the input gear first, which I'm assuming is the one that was earlier. So let's grab that one, bring that in. Okay, so the SolidWorks actually has fixed this gear. I'm gonna float it. I'm gonna float the gear, it's got a lot of sketching and stuff showing here. I wonder if I can turn that off. Okay, I've just suppressed some of the sketching in there so that we could more easily see what's going on. I've left one of the axis 1 here. I've left that where we could show that. So we're kind of in good shape here. I want to now mate this gear. And the way I'm going to mate it is I'm going to mate the origin of the gear with the origin of the assembly. And I'm going to do that in such a way that I'm not forcing the axes to align, just mating that one point and making it coincident, the origins coincident. So I'm happy with that. So what that should mean is I should be able to spin it about that one point. What I'm going to do is take this face now of the gear, and I'm going to mate that with the front plane of the assembly. Actually make that parallel. Okay. So now it's still underdefined, but I should be able to just rotate that about the central axis of the gear. So I think I'm in good shape. So it only has that one freedom now to rotate. Let's bring in the other gear, the later one. Open. And I'm going to do similarly. I'm going to suppress some of this other stuff here. Okay, so I've got my output gear all cleaned up, and I've got the axis 1 of the output gear. One thing I want to do is mate that that axis with the top plane of the assembly, because I know that the axis 1 of my input gear is in the top plane, since I put the origin align the origin of the input gear with the origin of the assembly. So I think I'm going to be good there, and I can actually come in and do a right side view of that. So yeah, I can see it. I can see that these axes are in the correct plane that I want. So I kind of have that going, but I don't have my center distances actually set. So I could put another mate in for that. What would the center distance be? Let's see, I've got bring up Excel. If I have a 3-inch diameter plus a 12-inch diameter, and I divide that by 2, looks like I should have 7.5 inches for a center distance there. So let me see if I can set the center distance between these two guys. Oh, I don't want them coincident. I actually want a distance there. Let me see if I can set that to 7.5 inches. So I have a good set there. Let's see. Let me look at a right view of that. So yeah, I'm looking like where I should be there. Pretty close. Oh crap. Let me rotate view. So I don't have them in the same plane, so I could set another mate here to put the faces in the same plane. So I'm pretty close here to what I want. Looking real good. But they're not geared together. You know, when I review my mates here, I'm looking at coincidence and parallel. I think that's okay in the distance, but it's really kind of hard to keep track of what these gears are since I have such a cryptic name. One thing I've done in the past is I might try to open a part and actually rename it. So here it's open. I'm going to try to save as. Copy will be in memory. Original file will be closed. All referencing files in memory will refer to the new name. So that's what I want. I'm going to call that input gear or whatever, just something I know what the heck it is. Oh, yep, let's save it that. Okay, I've actually done that for both the input and output gears, renamed them. So it's much easier to recognize what's going on. And as far as the mates go, I want to just rotate where I can get a sort of a good view here. For the mates, you know, I actually like to rename the mates too. So I'm going to call that origins, that mate, and the parallel. What is the parallel? That's putting input face front plane there. And then the coincident of the output gear with the top plane. This is center. Let's see, output axis on top plane. And distance, this sets the center distances between the axes. So I'll just call that center distance. Okay, and then I have the last one is the coincident mate with the output face with the input face. Okay, so I've just renamed them. Okay, one of the pains here is you really want to establish the two gears in such a way that there's no interference between the two gears, and if I do the interference detection, I can do the calculation and show that there's no interference. At this point, I can turn on a mechanical mate between the two gears. And to do that, I go assembly mate, and I come down here and do mechanical mate, and do a gear. And I need to establish the input axis. And the output axis. Number of teeth, so that would be 18, and this one would be 72. So it wants to put inches on there, but I think I'm good. I just put the gear tooth numbers there, showing 18 for that gear and 72 for that one. Let's see if it works. Gear mate 1. I'll say OK. Alright, let's turn it. Yeah. So it's actually doing what I think it should, and the teeth are meshing. So it looks like it's turning at the right speed and all. So I think we're in good shape there. It's still underdefined. So one thing I could do here is take one of the keyways, let's say that face, and I could make that face, mate that face, and make it parallel to the right plane. I think I can do that. Yes. So that's good. Gear mate 1, I'll leave that, but I'm going to set the name of this as gear input, sets the gear input angle. Initial. I'll say initial input gear angle. Okay. So now I'm fully defined. Okay, I put a lot of time into mates, and there's actually a reason for that. I wanted to show you a couple of things. First thing is I can actually go in here and suppress a mate. Some people don't know that. And when I do that, I can actually go back and turn the gears as I had before, and then I can go back and unsuppress that mate, and it snaps it back. So these things are good. And actually, I use the mates as initial conditions. Some of the mates I use as initial conditions in my motion analysis. For example, the input gear angle I'll use as an initial condition, and also the gear mate I will use as an initial condition. Usually what I do is I put all the mates that I want to be my initial conditions for my motion analysis, I put them at the bottom. That's just my way of doing things, and a lot of people don't know this, but you can actually move your mates around. Where'd he go? And I've moved my gear mate up, which I don't want. I just was showing you that you can do that. I'm going to put it back where it was. So, you know, even after you've created your mates, you can move them around so that you get your initial conditions, the things you want to be your initial conditions, down at the bottom. These others that I have, I'm going to let those run throughout the motion analysis, and those actually will act like constraints for the motion analysis. Okay, so again, I have my whole assembly set up correctly. I have my mates all squared away before I even begin to think about the motion analysis. Students fight me on this all the time, and then they realize I'm right later on. So let's go take a look at a motion analysis here. Let's bring up the motion study. Okay, so it comes up finally, and first thing you want to do is you want to get this pane set for motion analysis. Now, how do you have that? If you go to your toolbox actually Tools, and you go down to Add-ins. You need SolidWorks Motion checked in that place and also in that place. Okay, so I've got Motion Analysis in there, and it turns out that the initial view here is the one that I had before I created this motion study. So that's a point of reference. If you wonder how does it get that first view, that's how. Another thing is this slider. You want to have this slider all the way to the left before you start making any changes to your motion analysis. That's really important. And first thing I'm going to do is take this diamond, and I'm going to go to, let's say, let's go to 6 seconds. See what happens there. So I've just created a 6-second duration for my motion analysis. Then I'm going to come down here to mates. And remember, I was saying about the mates, the ones I'm going to suppress or I'm going to use as initial conditions. And the way you do that is you suppress it in the motion analysis. And I'm going to suppress the gear mate, and I'm also going to suppress the initial input gear angle. So you can see right now that they are suppressed, and that diamond means that you're turning them off right from the get-go, and they don't run throughout the simulation, whereas the others do run. Those are constraints. Okay, very, very important for that. Alright, so I'm starting to be in good shape here. One thing I need to do is to establish a motor. Let's bring in a motor, SolidWorks motor. And what I'm going to do is a rotary motor. And I'm going to fumble around here until I remember how to do it. So I'm going to pick that guy. Oh, not line. I don't think I want line. I want to pick... There you go, that face. That's what I wanted. What's this one do? Component remove relative to, well, that'll be ground. Constant speed, let's go 12 RPM. Okay. Good. Alright, I think I'm good there. Alright, so let's see, that's going to go counterclockwise. So that means my output gear is going to go clockwise. I'm going to put a load on my output gear. So I'm going to put a torque, and I want that clockwise, don't I? And my input gear is going counterclockwise, my output gear goes clockwise. Load opposes that, so I had it right. Okay. How much? Let's do 12,000 inch-pounds. See if it takes that. Yes. All right. See if that works. Okay, so I've got my rotary motor. I've got my torque running throughout. The last thing I want is solid body contact, which is this guy. Then I'm going to pick the two gears. SolidWorks forces you into this acrylic thing, which I don't believe has ever worked for me, so I usually switch to aluminum dry just to get going. This other stuff, if you unclick material, you can actually go in and change some of the other stuff. It will be ungraded where you can change it. So I'm going to go with aluminum dry and then pick and stay with the default values for that. So I'm going to say OK. I think I actually have enough stuff here to try to run it. This might bomb, I have no idea. So let's see if we can actually do a calculation. So to do that, well, you know what? I'm going to save this. Save. Okay, good. Now, let's calculate it and see what happens. Okay, it's done, and now I can actually play it from the start. And you see the input gear moving and the output gear moving. Remember now, this is not using the gear mate that we had earlier. This is actually relying on the solid body contact between the teeth in order to actually move the output gear. And the rotary motor is, with that input gear initial condition suppressed, the rotary motor is actually moving that gear, the input gear, at 12 RPM. And remember, we have that resistive torque that we apply to the output gear, the 12,000 inch-pounds. So what I've done is I've created a couple of plots. Let's show what the input gear is doing. So the input gear is doing what I asked it to do. It's turning, and unfortunately it shows it in degrees per second. But 12 RPMs does equate to 72 degrees per second. So it looks like the input gear is doing what it needs to do. Let's look at what the output gear is kinematically doing. Show plot there. Yeah, so the output gear is supposed to be going at 3 RPM. So 3 RPM is about 18 degrees per second. So it looks like it's doing the right kind of thing there. One thing I can do here is it started out at 0 and then it's ramped up to that. And you see kind of where the teeth are biting into the situation there. One thing I could do is go up here and do a right mouse, export CSV, and then let me output a CSV file there. And one thing I can do is go into my gears and open up that output gear and actually plot that, of course, here. And so let's see what that looks like. Oh yeah, so it's the same thing. So I was able to bring that in to Excel. Let me delete that. Actually, let's plot RPM. So I could say equals this. That's degrees per second. So I could go to rotations per second by taking that and dividing. Let's see. We would want to divide by 360 and multiply by 660. See what that does. Yeah, so we're right at about 3. And then let's plot that. So I could go A and C. And then I can insert a scatter line plot. So yep, right around 3 RPM. So that's looking good for the output. That sort of makes sense. Now let's see what is happening on the input motor. So over here, I'm going to show the plot. And again, you see where the teeth are kind of bumping in there. We're putting that 12,000 inch-pound load on the output, so we're kind of looking for a 3,000 inch-pound load on the input motor, which is kind of what we got. And again, I can take this and export a CSV and get my input torque motor. Input motor, let's go rotary motor CSV, let's open that. So this is actually going to be motor torque. Plot that. So yeah, it's right at, well, actually a little bit higher. That's crazy. Let's look at doing an average. Equals an average of B. See what that looks like. 32. So the motion analysis study is telling us that it takes 3,200 inch-pounds on the input to drive that 12,000 inch-pound load on the output. Theoretically, best would have been 3,000 on the input. So we've got a little bit like 200-ish more inch-pounds. Absolute, see, the relative error there would be about 8%. So we've got an 8% error there. Actually, we'll find out that we can get the efficiency here. So it's looking like there's a little bit of inefficiency. We can get the efficiency by taking the theoretically best input torque and dividing that by the actual input torque. So it's telling me I'm at about 92% efficiency. Remember, we picked that dry aluminum, so I think that's what's causing this inefficiency. If I get that better lubricated, then maybe I get towards the 98, 99% you usually have for spur gears. So anyway, this is kind of realistic here. So in summary, we set up a Solidworks motion analysis study on the two gears we got from Rush Gear. I emphasize that mates are critically important in the motion analysis study. And then I brought in a Solidworks motor to run the input at 12 RPM. I established a constant load on the output of 12,000 inch-pounds. Turned on solid body contact between the two gears and set that for dry aluminum. And then I validated the performance. I showed you how to generate some plots and look at what the output gear is doing in RPM, and then look at what load is being reflected on the input as far as torque on the input motor. And then we saw that, in fact, it was about 92% efficient due to the dry aluminum. So anyway, that's what we have for Solidworks motion analysis. Hope you enjoyed it.